The date is October 23rd, 1593. The governor of the Philippines had just been assassinated. A few days after setting off on a journey from Manila, his ship and crew were overthrown by Chinese pirates on board. When the news of his assassination reached the Philippines, the government was shocked. In the midst of all this panic, a new governor must be chosen. So, a meeting was held at the governor's palace. While business was taking place inside, guards were stationed around the outside to ensure the safety of everyone. This included many soldiers, including one named Gil Perez. After waiting outside and guarding the palace in the heat for what felt like an eternity, Gil decided to rest for a second. Nothing crazy, he stayed at his post, leaned against a wall, and simply decided to rest his eyes for a mere second. When he opened his eyes, he was in a place he didn't recognize. In literally the blink of an eye, he found himself in an environment that he had no knowledge of. He had no idea how he got there, wherever there was. Regardless, he continued doing his duties, watching out for anything suspicious. Except, he was the suspicion. The local soldiers and citizens began giving Gil weird looks. He was wearing the palace guard's uniform that no one had ever seen before. Gil was just a random soldier in an unknown location. Unknown to him, at least. That is, until the truth of the situation was brought to light. Gil Perez was no longer in the Philippines. In what seemed like an instant, he miraculously ended up in a plaza in Mexico City, over 14,000 kilometers away. Today, that distance could be covered in less than 24 hours. But in 1593, this voyage would have taken at least 2 to 3 months. Still shocked, Gil continued to explain his side of the story. He explained that he was a soldier from the Philippines, he explained how the governor had just been assassinated, except, of course, no one believed him. The problem here is, in 1593, it would be months before any news of this would reach Mexico City. He was immediately arrested for desertion and thrown in jail. A few months later, a ship from the Philippines finally arrived, carrying crew members as well as the news of the governor's assassination. And what they found out is that the story Gil provided matched up one-to-one with what the crew members aboard the ship were saying. On top of all that, several of the crew members actually recognized Gil, and were able to even recall the day where he seemingly disappeared from existence. He was set free, and returned to the Philippines to continue life as though nothing had happened. There's no real explanation for this story, it's over 400 years old. Many speculate that something paranormal had taken place, some suggest that he was just a liar. Others suggest that the story never took place and was just made up by someone. Some suggest that it was an alien abduction. But a few suggest teleportation. And that is something that I find very interesting. Teleportation is a common part of science fiction. Characters in video games, movies, and books can travel from one point in the universe to another without ever traversing the space in between. Faster than light travel, instantaneous travel. The implications of wielding a power this strong is unthinkable. But is there more to teleportation than just science fiction? The more we learn about our universe, the more science fiction starts to look like actual science. The idea of teleportation has been talked about since before the 1800s. However, it was Charles Fort in 1931 who first coined the phrase. He combined tele, meaning distant, and port, meaning to carry. Decades went by as the idea lay dormant in science fiction. Like, where do you even start with an idea like this? That was until 1993, when physicist Charles Bennett and colleagues proposed something groundbreaking. The quantum state of one particle could be teleported to another particle on the other side of the universe without the particles themselves really moving at all. In other words, information could be transferred across vast distances in space without physically having to move to that point. The team was able to take all the information of a quantum state, destroy it, transmit that information to another location, and then recreate the same exact quantum state as before. But before we dive into all that, let's take a step back. What are quantum particles? These are the particles at the subatomic level, and reality here is different from the reality you may know. There are many strange and honestly barely understood things that happen here. For example, particles can be at two different states at the same time, and until the particle is observed, both states are real and exist. Once observed, a final state is taken, forcing reality to collapse into one. This is known as superposition, and its most famous example comes in the form of a cat. Schrodinger's cat. Put simply, it's a thought experiment. There's a cat inside a box, and some radioactive material that has a 50% chance of decaying, poisoning the cat, and killing it. If the material decays, the cat obviously dies, but if it doesn't, the cat stays alive. From a quantum approach, until the box is opened, we can't know whether or not the material has decayed or not. The cat isn't dead, but it also isn't alive at the same time. Of course, this makes no sense in the real world, but at the quantum level, reality is different. This means that quantum particles can be in multiple states, rotating clockwise and anti-clockwise, at the same time, until an observer forces it to decide a reality, simply by observing it. But, let's say we recreated the experiment, but instead with 2 cats this time. Now we go from 2 options, the cat being dead or alive clockwise, to 4 options, where both cats can be alive or dead, or where one cat's alive and the other is dead, and vice versa. Quantum mechanics gives us a little bit of help here in cutting down these options. It says that there is a system where you can pretty much eliminate the options where both cats have the same outcome, either both alive or both dead. The only ones that matter are the ones that are opposite of each other. Because of this, you can open only one box and have 100% certainty of what is in the other box. But this can only happen when the cats are in a specific state, an entangled state. We now know that quantum particles can talk to one another, but only if they have a certain property to them. This interesting phenomenon in the quantum world is the reason that particles can theoretically be teleported. If they have this special kind of link to one another, they're what we call entangled. Entanglement is caused when 2 quantum particles are formed at the same instance of time and point in space. Hence, these particles essentially share an existence, and their connection is almost telepathic. They affect each other despite the vast distance between them. Quantum particles have spin. This doesn't mean they're actually spinning, but they have an orientation in space as well as an angular momentum. By measuring the state of one to be spinning up, or in the cat's case alive, it can be directly deduced that the other is dead or spinning down, despite it being on the other side of the room or the other side of the universe. They're linked from birth, and when one is observed, the other one knows exactly when. Einstein called this spooky action at a distance, and there is something fundamentally unsettling about scientific phenomena which are yet not entirely understood. Recently, scientists from China launched a photon receiver satellite into orbit. This satellite can detect quantum states of photons shot to it from the ground. From this, the longest ever distance of quantum entanglement was measured. But more importantly, this was the first time a photon was teleported from Earth into space. This works by transmitting the quantum information about one particle to its entangled pair. Therefore, the second particle would quite literally become the first particle. The research team created 4,000 entangled photon pairs per second. They shot half the pairs 1,400 kilometers up to the satellite, while keeping the other half of the pairs down on Earth. Over the course of 1 month, they sent millions of photon pairs to the satellite, and found success in only 911 cases. 911 out of millions of quantum pairs sounds like a huge failure. But actually, this is a very small but important step in teleportation. As scientists discover how quantum particles are used to make up matter, they could potentially find the keys to understand how to change these particles, in order to fundamentally change the matter itself. Rather than simply sending one encoded photon, could they one day send the exact construction of all the subatomic particles of, let's say, an apple? Perhaps, but with this comes a philosophical question. The teletransportation paradox dates back to 1775. The average cell in your body is, on average, about 10 years old. Some cells get replaced more often, while others, like the carbon-14 in your DNA, never get replaced. So considering most of your cells are not the same as they were when you were born, are you still the same person? If every single atom of a person was taken apart and reconstructed, is the resulting construction still the same person? We humans are simply a machine, where our DNA script tells us how to replace dying cells until either the script or the machine fails. But if this script of how you're constructed is downloaded and correctly transcribed, maybe it could one day be used to create new versions of you on the other side of the universe, effectively teleporting you. Wait, is this even teleportation? You're technically being recreated, as opposed to actual transportation. What about if you wanted to bring your conscience with you? If you wanted to bring the thing that for sure makes you, you? What if simply reconstructing you in another place doesn't cut it? For that, we need another option. One that won't destroy you, but simply relocates you. For that, we need to look at wormholes. In 1935, Albert Einstein and Nathan Rosen showed that, through the use of general relativity, black holes across the universe could theoretically be linked together by a tunnel through spacetime, a wormhole. Einstein's general theory of relativity states that the presence of mass or energy will warp the fabric of spacetime around it. I covered this in more detail in my dark matter video as well as some others, but I'll cover it here as well. A black hole has mass so dense that not even light can escape its strong gravitational pull. Scientists for decades have attempted to take pictures of a black hole. However, this has proven elusive because, well, light cannot escape, and the lack of light makes it essentially invisible, like you're trying to take a picture of nothing. But what about the light that doesn't get sucked in? What about the light that slingshots around the very edge of the black hole? This will make a light ring of sorts around the black hole. And recently, in April 2019, astronomers revealed the first ever image of a black hole. Einstein and his theories were proven right yet again. But what happens inside this hole? When we talk about holes on Earth, it's in the context of 3 dimensions, where someone walking down the road can fall downwards into an uncovered manhole, for example, which is basically a 2-dimensional circle on the ground. But in space, matter can fall into a black hole from all 3 dimensions. Black holes are pretty much 3-dimensional spheres. The shape changes a bit when supermassive black holes rotate at significant portions of the speed of light, but that's not really important. What is important is, where does this hole finish? I tend to think of them as funnel shapes, where a wide event horizon eventually tapers off into one infinitely small point, the singularity. But what if this wasn't the case? What if a singularity wasn't needed? If a link could take place in the bulk to take you to another part of the universe? Here, Einstein and Rosen theorized that the extreme density of mass may be enough to tear spacetime fabric itself and connect to another point in space, perhaps to another black hole. Scientists are unsure of what happens or if this is even possible. If it is possible, the chance of it randomly appearing in nature is pretty much zero. The center of a black hole is perhaps the most sought after but yet least understood point in science, math, and nature itself. Here is where the laws of our universe as we know them begin to break. But assuming that wormholes are possible, what's going to hold them open? What will prevent them from collapsing in on themselves, crushing whatever passes through out of existence? Math and nature. Dark energy is the reason why the universe is expanding at such an accelerated pace, and it just might be able to make wormholes much easier to create. Dark energy has an effect that is essentially like the opposite of gravity. Gravity pulls things towards objects with mass, but dark energy is a repulsive force. It has a negative pressure and tends to push. Imagine having a headache where it feels like your head is being squeezed, but instead of the squeezing being inward, it's pushing outwards. If wormholes exist and are capable of bending space-time in such a way to essentially allow teleportation between points of space, there's still many barriers to cross. We would have to figure out how to stop the intense gravitational pull from completely crushing our bodies, or perhaps the wormhole collapsing altogether. We'd have to figure out if a trip through a wormhole is a two-way street. If we go through, are we going to be able to come back? In 1988, physicist Kip Thorne proposed an idea where wormholes may be able to be kept open longer. He suggested that wormholes might be able to be kept open through the use of negative energy, but no one knew how to create this energy inside the wormhole in that very short amount of time that they'd be open. In his paper, Cambridge physicist Luke Butcher says that taking advantage of the Casimir energy that exists naturally in some wormholes could do the trick. After many calculations, he found that if you have a wormhole that's much wider than it is tall, so more like a worm slice as opposed to a wormhole, the amount of Casimir energy inside just might be enough to keep the wormhole from collapsing, just long enough to send a photon through. As with most things, the more we learn and figure out how things work, the more we realize that we don't know much of anything. More doors open up, more questions pop up, and not all of them have solutions. As you approach a wormhole, you'd be looking at a portal to another world. If you thought going to the moon or Mars was scary, traversing through a wormhole is essentially a suicide mission. The quantum world is strange and fascinating, as scientists uncover more about the secrets of the universe by studying its most basic levels. There are bound to be breakthroughs and leaps in technology. Teleportation may have been science fiction decades ago, but today, it may just be a point of theoretical discussion in a growing body of study. In the future, we may be reconstructing ourselves through entanglement and using wormholes as portals to explore once unexplorable parts of the universe. All good things come from compound interest. This includes friendships, relationships, finances, science. All of these things start out slow. When you meet someone new, you initially learn only the outermost layer of them as a person. As a kid, you have little to no money. In science, we have our basic fundamental models. But over time, these things build up, and the returns we reap increase as well. You connect deeper and build stronger relationships with people over time. The money you earn compounds over time to make you more money. The basic fundamental models that we have in science are used to discover new ideas, and those ideas help uncover even more ideas, making exponential progress. And that's why it's important to discuss topics like this. When it comes to teleporting humans and other objects, a question that comes up a lot is, will we have to have access to the other end in order to teleport there? Will we have to somehow reach that place, build a teleporter as a checkpoint of sorts, and continue to leapfrog around to other places, in our case the solar system, and eventually maybe even galaxies? With this, the more places we go, the faster we can exponentially expand. Compound interest. Sure, teleportation seems bizarre and unlikely to happen, but similar words have been said about things that have changed the world in the past century. The Wright brothers, who were pioneers of modern aviation, had their doubts about humans ever traversing the Atlantic Ocean in airplanes or blimps, but yet now we do this each and every single day. People believe that Henry Ford would bankrupt his company by trying to lower the cost of cars in the early 1900s, but look at any parking lot today and you'll see a Ford car sitting there. If you were able to ask anyone from 100 years ago, what would life look like in 2019? Not a single one of them would even come close to being correct. So I'll ask you, what do you think life will look like in 100, 1,000, 10,000 years? People, of course, will doubt any kind of world that seems too good to be true. And that's fine. I'll let history do the talking. I'll see you on the other side. Even though we don't completely understand this, we're using quantum mechanics and teleportation technology every day. Because of quantum entanglement, superposition, and quantum tunneling, we're building some of the strongest computing devices known to man. Quantum computers. Problems that would take normal computers years to accomplish can be done in mere seconds by quantum computers. Google, IBM, Facebook, and even government agencies are pouring tons of money and manpower into building these things. They can help create new medicine and technology to change the world. But when this falls into the wrong person's hands, it can be one of the worst things to happen to the internet. They can decrypt any message you send. They can decrypt anything thousands of times faster than a normal computer would. If you're browsing the internet unprotected, it will know, and it'll be able to find you. But if you're anonymous online, you'll be at a much lower risk of being a victim. ExpressVPN is your best option when trying to remain safe and protected online. For less than $7 a month, you can prevent yourself from credit card scams, online data tracking, and plenty of other potentially life-threatening situations. Every day when I turn on my computer, I automatically launch ExpressVPN and turn it on immediately. It's quick, easy, and to the point. You can forget about it and freely browse the internet in safety. If you're interested in staying safe while online, please check out expressvpn.com/aperture, where you can get 3 months of free encrypted protection. Online privacy is one of the most important things in today's world, so I highly recommend you stay protected at all times.